How's it going, everyone? Good to see you all. Another rendition of Trig, Volume 3. So we're going to get into one of the most important concepts of the entire class, and that is trigonometric functions themselves. So going to be quite a few derivations here at the beginning, proofs, if you will, on some of these things that we're going to be talking about in depth, and then obviously we'll do some examples and make sure we know how to use them. So I hope you will watch the beginning of this. I hope that it will actually help you to understand this even better. One of the most important sections of the entire class, not just the chapter, the unit, but the entire class. The first 3 chapters, very important, and this is probably the most important of the class. So we're going to talk about the Pythagorean Theorem, some of the other things that go along with deriving these trig functions, and some of the other very useful formulas such as the Pythagorean theorem and the distance formula that we will be dealing with. And as you can see, I'm going to be going over one of the Pythagorean theorem proofs. I'm going to start with that first. There's nearly 400 original proofs of this. I'm just going to give you a very simple one, starting with this square. So I'm going to start by drawing in this square some length. And let's say that this is a length of A, and I'm going to do that everywhere, that same length. And I tried to draw that as close as possible to being the same. Next, I'm going to do another length of length B for every other length of that square. And so now we know we have a distance of A plus B. And hopefully you remember that the length of every single one of these being the same, we know we can find the area inside. All of this space, this area inside, is simply just the length times the width, or a side times a side. So in this case, that would give us an A plus B squared, or A plus B times A plus B. And if we FOIL or multiply this out, we get an A squared plus an AB, and then another to give us 2AB plus B squared. So we know the entire area of this inside here is all A squared plus 2AB plus B squared total. And what I'm going to do now is I'm going to actually cut this up. And I'm going to tell you that from this point, that splits up all of these A's and those B's, I'm actually going to draw a length from each one of those. And because every single one of those now, hopefully you can see, looks like a triangle. So this has a length of A and a width of B at that right angle there. And then this has a length of A and B and A and B and A and B for every single one of these. Which means that all of those red lengths that I just drew in were some other length, but they were all the same. So I'm going to call those C. And then that enables me to find the area of the inside of this, which is also a square. And that square there would actually be the same type of idea, a length times a length, or a side times a side, which in this case we're calling a length of C. So C times C, or C squared. But there's also some other area in there that I need to find. And each one of those, as you guys can all see, no pun intended, are right triangles. And every single one of those are all the same. And so we also have this additional 4 triangles, which hopefully you remember how to find the area of a triangle. It is 1/2 the base times the height. And since each one of those has a base and a height that are the same, of either that A and B, no matter which way you look at them, I can then say I have 4 of the same, one with an A and the other with a B. And since all of this is asked to be multiplied together, I will then have my C squared for that inside, plus I will have that 4 additional triangle areas that we said we would also have, which would be this one, this one, this one, and that one. And together you can see that I've now found the entire area on the inside with that one square and those four triangles, which therefore has to be equal to the a squared plus 2ab plus b squared. And when I do that, I know since I'm multiplying all of this together, the only things that I can actually multiply together is the 4 and the 1/2. And you all know what half of 4 is. That would be 2. So we get 2ab. And therefore we know that these are equivalent. And if you can already see, there are things on either side of that equal sign that are already the same. So what I'm going to do is I'm just going to subtract the 2ab from both sides so that those will then cancel out. And what I'm left with, you may recognize. I would have a squared plus b squared on the left side, and that's all equal to c squared, which is our Pythagorean theorem. So cool little proof just to kind of show you where, one of the reasons why we now know this to be true. And therefore we call it the Pythagorean theorem, who Pythagoras himself actually was not the one that came up with this, but gets the notoriety. It's actually one of his students, so I'm counting on you. So in this case, you all know hopefully the main parts that you have to pay attention to in the Pythagorean theorem are the a and the b. Those are your two legs, here and here. And therefore the one that you should pay the most attention to is the c squared. That's the one we call the hypotenuse. We give it a special name because it's always the longest side, which is opposite the 90-degree angle. Okay, so cool little proof there. Hopefully you enjoyed that. Next, we're going to get into the distance formula. Now that's not one that we use as often, but I do want to also derive that for you. So I'm going to start by taking these two random points. And I'm going to actually take this and I'm going to find a third point right here, which if this point P, we're calling it, is the point x1 comma y1, and then this one was x2 comma y2, then I could say that this third point, let's call it R, which is a distance from there and straight down there. And notice I have now created a right triangle. Now, that's one key thing about Pythagorean theorem. We have to have a right triangle in order to use this formula, which we will then utilize here in just a minute. But can you give me the point, the ordered pair for that other third point that we created, R, between P and Q? Because right now our task is to find the distance, that variable right there, D, between those. And if I can actually come up with the distance between P and R and Q and R, then we can use the Pythagorean theorem, because then we will have our two legs and we can then find our hypotenuse, we're calling D. All right, so to go over, how far would we have to go over from the origin to the right to get to this point R, we are calling it? Well, if you notice, we'd have to go over the same we did with Q, which is our X value. So in this case, we know that it would be the same as X2. Now, what about our Y value, our height? Well, from the origin, we know we'd have to go up here. And instead of going over this direction or that direction, we're going the same as P as we are R. So in this case, since that is what we called Y1, we would go up the same as that one. So this would be called Y1. And so if we wanted to find the distance between these things, then we know the distance or difference between P and R would depend solely on X2 and X1, the change in our X's. So that would be, we're going to take the bigger one, which is X2, and we're going to find the difference between it and X1. And then we're going to do something very similar with the y values to get this distance. We're going to find the difference of that y value and that y value. And I'm going to take y2 first and subtract y1 to find the difference so that I get something positive. Now, it doesn't always have to be that way, so we're going to have to make sure that it is by squaring it. But now, hopefully, you can see that we have everything we need. We have a leg, and its quote-unquote known distance, and then we can say that we also know what that distance is. And we can set up, using our Pythagorean theorem, our a squared plus b squared equals c squared. And that would be x2 minus x1, y2 minus y1 for our two distances, our a and our b. And then our last hypotenuse, which remember is always opposite the 90-degree right angle, would be d. Now the problem with that is this is set up to actually be equal to d squared. We wanted to know what d by itself was. What is that distance between these two random points p and q? So hopefully you know how to undo squaring something. We would have to take the square root. And if we do it to one side, we'd have to do it to the other. Now the whole thing, okay? Be careful with that, because a lot of you guys know 9 plus 16 is equal to 25. That's all a true statement, right? But if I wanted to try to take the square root of this thing, you got to be careful, because if I take the square root of each individual, let's see if it's still true. We know the square root of this is 5, 4, and 3, and this is no longer a true statement. But if we would have just taken the square root of the whole thing, then we would have had 25, just like we have over here. That's underneath the root, and now it would be true. Okay, so that's why, unfortunately, we have to square this whole side over here, because we're squaring this whole side. And that all was done so that we can find the distance between two random points, P and Q, at x1, y1, and x2, y2. So it is simply the square root of the difference in your two x values squared plus the difference in your two y values squared. That, my friends, is what is called the distance formula. And it is derived from the Pythagorean theorem. Okay, so keep that in mind. Pretty cool, very easy to understand. If you were able to follow along with that, awesome. But more importantly, make sure you know how to use these two formulas. Okay. Before I move on, I also wanted to mention these things that are called Pythagorean triples. Pythagorean triples are three sets of numbers that make this Pythagorean theorem true, but in such a nice way that it's important for us to actually memorize them. And you guys may be familiar with the most commonly seen and used Pythagorean triple, and that is the 3, 4, 5 Pythagorean triple. Now, don't forget, and we'll talk about this as we move forward, with similar triangles, we can actually have some ratio of our side lengths without changing the angles. So we can have twice as big of side measurements, like a 6, 8, 10, or 10 times as big, a 30, 40, 50. So you may see this 3, 4, 5 in different forms. Just make sure that you know that that is still something that we can use without having to go through and do the entire Pythagorean theorem to find one of those three unknowns. They have to give us two. The other types, 5, 12, 13, and 8, 15, 17, and 7, 24, 25. And there's quite a bit up to 100 if you want to look them up. But these are the main four, with the main one being the 3, 4, 5. So I bolded that in red, gave you the other three here. All right. So we've worked our way up to where we're headed, and that's trigonometry, meaning we have to actually define what trigonometry is. And so there are 6 trig functions that we're going to be dealing with, and they are sine, cosine, tangent, and then what are called their reciprocal functions, which we'll get into, cotangent, secant, and cosecant. And because those are quite a lot to write, and mathematicians like to use abbreviations, we will only take the first 3 letters of each one of those. Okay, now don't forget the key to this is they're of some angle. We have to have some angle. And so I've started by drawing that down here for you and going from O to P. So if I was to actually want to deal with this, I need the angle. I need the, we called it a initial side. And so I'd have to go from O all the way over here, and then I could rotate that up to make that angle. And so I need a reference. I need that bottom part. And so what I'm going to do is actually keep that, and I'm going to drop from that point P straight down to my x-axis. Now we could have chosen to go to the y-axis, but we did the x-axis. It was called the number line when we were first learning numbers in math. So since we did this first, we're always going to drop it to the x-axis rather than to the y-axis ever. Okay? Now notice when I drop that straight down, I've created what is called a perpendicular, a 90-degree angle, which is really important because now we have a right triangle. And since I was trying to form that angle right there, we call that theta, remember? How could I get to that point? How far over and up would you have gone to walk out to that? And we're going to talk about this in several different ways throughout the course, but right now you know this as an ordered pair, and you would have gone over some x direction here, and then from there you would have gone up some amount of y. And we call that x and y because those are the axes that we labeled them as. This was our x-axis and this was our y-axis. Which means that this down here would actually be a distance of whatever we call it, x. And this would be some distance y. And therefore, if I was to take this line we called OP, and I was to swing it around to there, what if I kept going with that same length all the way around, either to the x-axis or to my point? What would I have just formed by doing that? And hopefully you said a circle, which is why we are going to call this the radius, r. And therefore you should also see that we can take this x squared plus y squared, 2 legs of our right triangle, and set it equal to our hypotenuse, our r squared, and there is our Pythagorean theorem in use in creating what is called a circle. Okay, that is the formula for this. To get to any point on that circle, we would use that formula, that equation. Okay, so what we are going to do is actually label these things. We're going to define them right now. If I want to take the sine, now remember, you need an angle. It's of an angle. I can't emphasize that enough, because if you just write this, that's exactly what it is, a sin. Okay, you have to make sure, even though we're getting rid of all but the first 3 letters in each of these trig functions, with the exception of this one, because COS is already taken, we will write CSC for that one. Okay, other than that, we need the angle. So when we find the sine, cosine, tangent, let's just start with the first 3. I want to know what that is equivalent to. When I have that angle, what am I going to get out as a ratio? Right? And a lot of you probably remember from high school, SOH, CA, TOA. And that stands for each one of our trig functions, sine, cosine, and tangent. It gives us what it's equivalent to as a ratio. So that would be opposite over hypotenuse. Now remember, the hypotenuse is always here and opposite to this angle there. So for sine, it would be the opposite, which would be y, over our hypotenuse, which would be r. Cosine is the adjacent over hypotenuse. So if you don't know what the adjacent is, you should know what the hypotenuse is, and you should know what the opposite is. So in this case, we already know all three sides because we know to here, that's the opposite side. And this is opposite the 90, so that is the hypotenuse. Therefore, to this angle right here, we know that this piece right here is the adjacent side. So for cosine, which is the ca adjacent over hypotenuse, we know it's going to always be x over r. And then tangent is the opposite over adjacent, which we are going to then label always the y over the x. And so these are what we call the big three. And you want to be able to memorize each and every one of these so that when we call out what is sine, you know it's y over r. What is cosine of some angle? Well, it's equal to x over r. And what is tangent equivalent? It's y over x for that angle theta. Okay, because if you memorize those big three, then the other three are very, very simple. You're just going to have to memorize which go with what. And so sine, its reciprocal function is cosecant. Cosine is secant, and tangent, the easiest one, is cotangent. And we call these reciprocal functions because that's all they are the reciprocal of each one of these ratios that we got out. Y over r, the reciprocal of that would therefore be r over y. Secant, r over x. And cotangent, x over y. So these are our 6 trig functions that we will continually use throughout this course in more detail and in more scenarios. Okay? And hopefully you recognize that with each one of these, I wrote down here, each pairing actually has a co-function. And that's another thing that we will talk about as we progress. There is sine theta and cosine theta. There is tangent theta and cotangent theta. And there's also secant along with cosecant. And so those are the types of things that we will get into as we progress. But for now, remember your SOHCAHTOA that you can then use to now label these things in terms of X, Y, and R, because that will come in more handy as we progress through. Okay, so I have all of that written down here, along with, and this is for your notes, along with some things that we have to be careful of. Because these are fractions, we have to be very careful to make sure that we do not have values that are actually equal to 0. And we'll talk about that right now. So don't forget that. And remember, we just discussed how to get from this point to that point would be the rise over the run, or the y over the x. That's what we call the slope. And if you notice, we have y over x right here. It's actually equivalent to tangent. And that's something that you will talk about a lot in calculus, is slope, what it means, and then actually finding the slope of a tangent line. So all of that is connected when and hopefully if you guys get and have to take calculus. Okay, so again, these are things that you have to memorize, which remember came from our 2 derivations up above of the distance formula, which was rooted in Pythagorean theorem. So a couple more things, then we'll get rocking and rolling on the first example here. One more type that we're going to deal with is called a quadrantal angle. Okay, we talked about these last time. What is a quadrantal angle? Well, remember, that's when we land on one of our 4 quadrants, either at this point, this point, this point, or this point. And again, if I was to connect all of those points, like so, you can see I would get a circle. And so therefore we know that that is equivalent to x squared plus y squared equals r squared, with us having a radius of 1, because it's the easiest one, so we might as well use 1 if we have the choice. And so with all of that, these quadrantal angles, we have to be careful when we are on those, because like we just said, we have to be very certain that each one of these, when we evaluate for some angle, like 0 degrees, 90 degrees, 180, 270, or even back all the way around at 360, one of our 4 or 5 technically quadrantal angles, then that means a 0 is involved. And when we have a 0 involved, we have to be very, very careful, because here my y is 0, as is here, because we're along the x-axis. And when y is 0, we have issues. We have issues here for cosecant and cotangent. And we cannot divide by a 0. We don't know how. So when we have a quadrantal angle, instead of saying some random angle like theta, what if I had the sine of 180 degrees? Remember, sine, we said, is always the y over the r, and at 180 degrees, I'm right here. And I know the y value, I know the r value, it's 0 over 1 or negative 1, which is fine. We can take a 0 and divide it any number of ways, positive, negative, whatever. Our answer is 0. But if I was to ask you to take the reciprocal of that, cosecant, which is just flipping that and getting therefore r over y, that means I'd now have negative 1 over 0. I can't take any number of things and divide it 0 ways. So in this case, we'd have to say it does not exist. There is no ratio for that particular angle and trig function. All right? So be very careful with these quadrantal angles. Because the zeros are involved, we will have issues. And since there are issues, we want to try to make sure that we memorize these as well. The more you memorize now, the easier this class is going to be as you progress, especially at the end. But now, if we're at 90 or 270, meaning we're along the y-axis, you can see that now our x would be 0. And we said there are certain things that also have issues when our x is in the denominator, 0. Notice those are all of the things that are not sine and cosine. Of our 6 trig functions, sine and cosine are our absolute favorites because they don't have the issues that some of those other ones do. So when we're trying to work in our trig land that we're going to be dealing with and adding more and more things, we're going to be talking about sine and cosine the most and first, because they're the easiest to work with. They don't have those issues in the denominator because they have r in their denominator, which is the radius of 1. And without the radius being anything, then we don't have any direction. We don't have an angle. We're just at the center point, the origin of our axes. So that's why sine and cosine are really nice, but not so much for the other 4. Okay, so be careful with those quadrantal angles. That's it for this round. We'll keep talking about this and going into even more detail with it as we progress through. But now let's get to the examples. And here's the first. It says the terminal side of an angle theta in standard position passes through the point 12, 5. And you need to know what 12, 5 represents. And hopefully you said the point. But that's not my point, okay? The point I'm trying to make is they actually are telling you what x and y are. And if we know 2 out of our 3 sides of a triangle, then we can find the third as long as it's a right triangle. we can use that Pythagorean theorem. So in this, they're asking us to find the 6 trig functions for that angle, theta, that they told us to get to that 0.12, 5. So can you see what we're dealing with here? Absolutely not. What do you need? Yeah, hopefully you said we need a drawing. So that's the first thing I'm going to start with. I'm going to draw my 2 axes. And again, they said starting on the origin and passing through that 0.125. So what I'm going to do next is I'm going to draw that point from my origin going to 12, 5, which means I'm going to go a length of 12 here, and then I'm going to have to go up a length of 5. And that's going to get me to that point that they're calling P, or whatever you want to name it. You don't even need to name it. But you know that you've just created, by walking right 12 and up 5, a right angle. And remember, this class is called trigonometry for a reason. It's the geometry of triangles that we're studying the most. And so I'm just going to simply complete this and draw my right triangle. Because now I have what is called a right triangle that allows me to use the Pythagorean theorem. So I will do my a squared plus b squared equals, we're going to call this r, we're going to call this x, and we're going to call this y, so that we can start memorizing these things. The sooner the better. If you need to make flashcards or whatever, do it. And remember, we need to know r, because what they asked us to find were the 6 trig functions. And so we're going to have to end up finding sine of that angle, which I'm going to label theta, cosine, and tangent. And I'm actually going to stop there, because when I know those 3, then I actually know cosecant, secant, and cotangent is simply the reciprocal of those. So once I find my big 3 here, then these other 3 will be very easy to find, because they are just the reciprocal of the originals. Okay, so I need to find r first. So in order to do that, I'm going to square 12, which is 144. I'm going to square 5, which is 25. And then I'm going to add those together to get 169. You know what? I don't even want to do this. I can actually skip this step, because I took the time to memorize and recognize that this is actually what is called a Pythagorean triple. 5, 12, 13, which then allows me to bypass having to actually do the Pythagorean theorem. Now, it's not that much more work. We were almost there. All I would have had to have done last is take the square root of both sides to get that r by itself, which is then equal to positive or negative 13. But we're going to only take the positive case because this is a radius. So now I have everything I need. All I need to do is make sure that I start memorizing what sine is equal to, cosine, and tangent. And then I can do the reciprocal to find the other 3. So sine theta, we said, was y over r, and we said that y was 5, and we had to find r. Since that's 5 over 13, I also know cosecant is the flipped ratio, or reciprocal. Now, one way a lot of people get cosecant and secant messed up. They think cosecant goes with cosine and secant with sine. I just read it from right to left. Now, I know that doesn't help you with cosecant because it's still CSC, but I almost see cosine right there. This kind of looks like an O. So I recognize that this is actually cosine. All right. So whatever helps you to memorize that, once I find cosine, which I memorized, is x over r. So I'll take the x, which was 12, and the r, which we found is 13. I can then do the reciprocal and find that secant is therefore 13 over 12 for that angle theta. And then lastly, we would have to find tangent, which tangent, remember, was the y over the x, and therefore cotangent would be the reciprocal, which would be x over y. Right? And that therefore is example number 1. Now, I'm going to warn you, drawings really help you to not only visualize, but work through these problems. So I highly suggest, even though they just give you a short paragraph or a couple sentences, draw out whatever they're giving you.